What if the same trick that lets a quantum computer find a needle in a haystack could also let us sculpt perfect many-particule entanglement on demand? That provocative idea is no longer science fiction. A joint team from the University of Wisconsin-Madison and the University of Copenhagen has just shown that Grover's famous search algorithm, yes, the one you probably met in a textbook as a way to speed up database lookups, can be repurposed to carve delicate, multi-atom entangled states inside an optical cavity. But here's where it gets controversial. Some physicists argue that Grover's algorithm is too fragile for real hardware, while others claim this new twist might finally make large-scale entanglement practical. Who's right? Keep reading, then jump into the comments and tell us which side you're on. Why should you care about sculpting entanglement? Imagine trying to tune 500 atoms so that every single one shares the exact same quantum whisper. These collective states, Dicker states, GHZ states, and the legendary Schrödinger cat states are the fuel that powers next-gen quantum sensors. Think GPS-free navigation, error-corrected quantum computers, and hack-proof quantum communication links. Until now, creating them has been like trying to balance a pyramid of champagne glasses during an earthquake. Either the success probability is painfully low, or the slightest noise shatters the whole structure. Enter the optical cavity, a microscopic hall of mirrors that traps light so effectively that a single photon can bounce back and forth thousands of times before it escapes. Researchers have long known cavities are great at talking to atoms, but coaxing them into producing large, error-resistant entanglement has remained stubbornly difficult. Grover's algorithm, as a sculptor, not a search engine, Love Grover's 1996 algorithm is usually introduced as a way to find one marked item in an unsorted list, with a quadratic speed-up over classical computers. The Copenhagen, Wisconsin team realized that the very same amplitude amplification trick can be viewed as a sculptor's chisel. Each reflection of a single photon off the cavity gently nudges the joint state of the atomic ensemble closer and closer to the desired entangled target. After at most 8 photon bounces, the atoms are locked into a pristine Dicker state, even when the ensemble contains up to 500 atoms. 8 photons, 500 atoms. Let that sink in. And this is the part most people miss. The method is not married to atoms in a cavity. The authors explicitly show that superconducting qubits sitting in microwave resonators, trapped ions chained together, or even neutral Rydberg atoms hovering in laser tweezers can all benefit from the same Grover-based recipe. In other words, the approach is platform agnostic, a rare luxury in the often siloed world of quantum hardware. A quick tour of the states you can now dial up on demand. Dicker states. Symmetric superpositions, where a fixed number of excitations are shared evenly among all atoms. These are gold standards for quantum metrology. Imagine measuring gravity gradients with unprecedented precision. GHZ states, the famous all up or all down superposition that makes even Einstein uncomfortable. They're the backbone of many quantum error-correcting codes. Schrödinger cat states, macroscopic superpositions that let you test the boundary between quantum weirdness and classical reality, while also serving as logical qubits that resist certain types of noise. The fine print, and why some researchers are raising eyebrows. No breakthrough comes without caveats. The protocol demands cavities with extremely low photon loss. Even a tiny leak can scramble the delicate interference pattern that Grover amplification relies on. Experimentalists know that building such ultra-high finesse cavities is non-trivial. It's a bit like constructing a mirror that stays reflective after being polished to atomic smoothness. Naguib himself admits that relaxing this requirement, perhaps by embedding active error mitigation steps, is the next frontier. Bold question for the community: is insisting on ultra-low loss cavities a reasonable engineering target? Or should theorists pivot toward algorithms that tolerate more realistic, lossy hardware? Drop your hot take below. What happens next? The team has already sketched out extensions that could prepare an even broader zoo of entangled states, including cluster states for measurement-based quantum computation. If those ideas pan out, we might see Grover's algorithm evolve from a textbook curiosity into the workhorse of quantum state foundries. So is this the moment when Grover's search finally graduates from classroom example to industrial tool? Or will the skeptics be proven right that the hardware hurdles are insurmountable? The debate is wide open, and your voice matters. Let us know. Would you bet on cavities? Or do you think another platform will crack scalable entanglement first? Article written by Ingrid Fideli, edited by Gabby Clark, and fact-checked by Robert Egan. Independent science journalism survives only with reader support. Consider a monthly donation to keep these deep dives coming and enjoy an ad-free experience as a thank you. Further reading: Omar Naguib et al. Efficient Preparation of Entangled States in Cavity QED with Grover's Algorithm. Phys Relay Let. 2025. DOI 1010350F WSR2. Deterministic Carving of Quantum States with Grover's Algorithm. PhysRev A 2025. DOI 10103/S3VSXZW. Preprint available at Archive 2501881. Copyright 2025 Science X Network.